Quantum mechanics says that a particle is a particle and at the same time it is also a wave. A wave is a wave and it also is a particle. This is a particle, it also is a wave. Light is a wave, it also is a particle. That's weird, it's ridiculous. And you know what is even more ridiculous? Even more ridiculous is the fact that it actually is true. That's the way nature works. A particle is a particle and a wave. A wave is a wave and a particle, both. So everything is both particle and wave. Okay, so an electron is a particle, at the same time it is a wave. An atom is a wave. A material is a wave. Can you believe that? Who can believe? There has to be some way to ascertain this, to prove this. Okay, light is a wave. We proved it. Okay, it's not that some scientist said that light is a particle and we believed. Some other scientist said that light is a wave and we believed. No, that's not how science works. Okay, in science you have to have a proof that is undeniable or irrefutable proof. Okay, now so what was the irrefutable proof that proved that light indeed is a wave? It was YDAC. Okay, it is the Young's double slit experiment that we studied in interference. Okay, so what is this Young's double slit experiment? Okay, well, we have this two slits and light beam. The light beam, a parallel light beam is incident on these two parallel slits. Okay, two slits, and on this screen what I see is I see this alternating bright fringe and dark fringe. There is a bright fringe here. Okay, then I have a dark fringe here. Then again a bright fringe. Okay, dark fringe, bright fringe. Okay, dark fringe. Okay, like this. This we call as. Okay, so and this is how the intensity changes. Okay, this is fringe pattern. Okay, so if I do this experiment, so on this screen I am going to get fringe pattern. This can be explained only with wave nature. There is no other way. You cannot explain this behavior using the particle nature of light. So this experiment and diffraction experiment, both we have studied. Interference, YDAC and diffraction. Both these experiments established firmly the fact that light is a wave. Now what quantum mechanics says is that in the same manner an electron is also a wave. Now if an electron is also a wave, then it must produce this interference pattern here, a fringe pattern. Is that possible? Okay. So let's say that instead of light beam, let's bombard this setup with electrons. Okay, with electrons. Okay. So instead of light beam here, I have parallel beam of electrons. Okay. These are my electrons, fast moving electrons like this. Okay, what are they? They are electrons. Okay. Now, what do we expect? Forget about this chapter. Forget about wave-particle duality. Forget about the electron acting as a particle or a wave. Forget about it. Use your common sense. Common sense. I have this stream of particles, a beam of particles. Okay, and I have these two open on this screen. What do I expect? Okay, I expect that at this point I should find electrons. I should find electrons, and at this point here I should find electrons. So I should find electrons here, and I should find electrons here. I should not find any electron here. No. Electrons here? No. Here? No. I should find electrons only here and here. This is what? This is our expected result. This is what we expected. And this is what every scientist expected. Okay? When this debate was raging, whether this theory is correct or not. Everyone expected this. But do you know what was actually observed? Okay? What was actually observed is not this, but actually a fringe pattern like that of light here. Okay? So this was the actual electron was observed everywhere. At some point, no electrons were observed. At some point, the maximum number of electrons were arriving. Okay, so here also we got fringe pattern, and then everyone was like shocked. Every scientist was shocked. Okay, that means electrons are behaving like electron is a particle. This particle is behaving like a wave. Okay, and this was a groundbreaking experiment. Groundbreaking. It changed every concept. Okay, it overturned every concept. Now the same experiment was carried out with other particles, with protons, with neutrons, even atoms. Not even atoms, but big molecules. Okay, the molecules that we call as buckyballs, Buckminster fullerenes. Those big football-like molecules. Every time the same result was obtained. Okay. Now, if this electron is behaving like a wave, then it must have wavelength. Okay, so this electron here is behaving like a matter wave. This is known as a matter wave. A matter wave. Okay. Then what is its wavelength? What is its wavelength? Okay, its wavelength lambda is given by h over p. It actually has a wavelength. Okay, this is lambda h over p. This is known as de Broglie wavelength. Okay, de Broglie was a PhD student, and he submitted this. He theorized this thesis. Okay. Theorized it before this was done. Before this was actually done, he theorized it. De Broglie theorized it in his PhD thesis when still he was a student, and it was found to be correct. Okay, and this put quantum mechanics on a very firm, solid foundation. Okay, now this is known as the so every particle having mass momentum is going to have wavelength associated with it. It is given by de Broglie wavelength. Okay, what is h? H is Planck's constant. Planck's constant. Okay. What is it equal to? Is it equal to 6.626 and 10 minus 34 joule second? Joule second. Okay. Now P is momentum. P is momentum, and this lambda is wavelength. Wavelength. It is also known as de Broglie wavelength. De Broglie wavelength. Okay, so this is how matter behaves like a wave. Now, what about the other aspect? Wave behaving like matter. Now, this has a very interesting history. Okay, note it down. This is our first concept, de Broglie wavelength, lambda h over p. Okay, this is what is this? This is matter behaving like a wave. Okay, now the second aspect, wave behaving like a matter, wave behaving like a particle. Okay, wave behaving like a particle. Well, we started this chapter on interference. We discussed a little bit about the interesting story of light. Okay, people struggled for thousands of years to find the nature of light. Some people thought it was particle, especially the Greek philosophers in the beginning. They thought it was particle. Then Newton thought that it was particle. Okay, Newton thought. Okay, let's start with him. Newton thought that it's a particle. Okay, light. About light. Light is also a wave. Light is also a wave, electromagnetic wave. Okay, so light also behaves like a particle. That's what this quantum physics says. Okay, let's see. A brief history again. Okay, Newton believed that it's a particle. Okay, then came Huygens. Huygens believed that it's a wave. And then, assuming a light to be a wave, he explained many things. He explained reflection, he explained refraction, interference, diffraction. Newton explained reflection and refraction. Okay. In his time, Newton's time, this phenomena of interference and diffraction was not observed. Let's say it was not known. Okay, so he did not have to bother to explain that. Okay, had it been observed, Newton's theory would already have been discredited. Okay. But then at that time, fortunately, it was not discovered, so Newton theory, it held for some time. Then Huygens came and he proposed his wave theory. Now, he was able to explain. Okay, then we had YDAC and diffraction experiments. Diffraction experiments. Okay. Now, all of them concluded that light is a wave. Light indeed is a wave. It was firmly established. Finally, okay, that this interference and diffraction is a property, is a nature of waves only. Okay, that means light is a wave. Okay, but the surprise was not yet over. Okay, the climax was yet to come. Now, what was the climax? Okay, the climax was black body radiation. Black body radiation. Okay, it was observed by Kirchhoff's et al. Okay, and then photoelectric effect. Okay, Leonard, Hertz, okay, etc. Okay, many people were involved. Okay, many people observed this phenomena. Okay. Now these two phenomena, okay, could not be explained using wave nature of light. Using wave nature of light, these two phenomena could not be explained. Again, everything was disturbed. Okay. By this time, people were sure that light now is a wave. Everyone accepted. But then came these two important observations. Black body radiation, photoelectric effect. It could not be explained using the wave nature of light. Okay, then what was done? Okay, what was done? Okay, Planck explained black body radiation, assuming that, okay, what did he assume? You know what he assumed? By assuming that EM waves that energy of, assuming that energy of EM waves is quantized. Okay, that means in small packets. Okay, in the units of is quantized in the units of E is equal to h nu. Okay, where nu is frequency of light. So if I have an EM wave, if I have light, X-ray, any EM wave, so its energy is not continuous. It is actually in discrete packets. Okay, and the energy of one such packet, very small packet. Okay, he called it quanta. Okay, so energy of one such small packet is equal to h nu, frequency, where nu is frequency of that light. Okay, so assuming this, Planck was able to satisfactorily explain this black body radiation. But you know what? He did not believe in it. Planck did not believe in it. Okay, he considered this as a purely mathematical concept, a purely mathematical trick. He considered this thing as only a trick, having no actual physical reality. That's what he considered. Planck, who proposed it, did not believe in it. He thought that this is just a mathematical trick. This is a trick which explained black body radiation. But you know what? Einstein believed in it. Einstein believed in it. Okay, so Einstein explained photoelectric effect okay, on the basis of quantization of energy. Okay, EM waves, quantization of EM waves. Okay, the same concept, E is equal to h nu. Okay, so he said that no, this is not just a mathematical concept, this actually is a reality. That's how light actually works. That's how nature works. Okay, so we can think of EM wave light as a stream of these packets, these quanta, small packets, each packet having this much energy. Okay, and one quantum, one packet. Okay, one packet, a quantum of energy. Okay, quantum of energy. Quantum of energy of an EM wave is also called a photon. Okay, a photon. A photon means one quantum. One photon is one quantum, the smallest unit of energy. Okay, so one quantum of energy, one packet of energy. That packet is known as a photon. Okay, so energy of photon. Okay, E is equal to h nu. This will become hc over lambda. What is this? Where is this coming from? Okay, let me clean all this. Okay, let me clean all this. Okay, so we have this forward wave. Speed is equal to frequency times wavelength. Okay, so this V is equal to, so for EM wave, the speed is c is equal to nu. We are using this nu symbol here. Nu. You can use f if you want. That's not a problem. And lambda. Okay. So nu will be equal to c over lambda. Okay. So that's where this is coming from. Okay. Now, so photon. Understand this. Photon is now a wave. It's part of wave. It is a particle also. Photon is a wave and particle. It's like a packet inside which waves are packed. One imaginative way of thinking. Just imaginative way. Otherwise, even Einstein could not actually fully comprehend the nature of photon. Okay, and then you can guess. If Einstein couldn't do it, well then it makes no sense me saying anything about it. Okay. All right. So energy of photon is this. Now this also acts as a particle. Okay. What will be its wavelength? Okay. Now if I apply de Broglie, okay, what is momentum? Momentum of photon. Okay. P is equal to h over lambda. De Broglie relation, de Broglie wavelength. Okay. Makes sense. What is momentum? M times c. Momentum is mass times speed. Momentum is mass times speed is equal to h over lambda. Is that fine? Is that fine? Okay, now what is h over lambda? What is h over lambda from here? It is equal to E over c. E over c is momentum. Does it remind you of anything? Momentum is E over c. Does it remind you of anything? Remember EM waves. EM waves. This relation was given by Maxwell. Momentum carried by an electromagnetic wave is equal to this E over c. In that chapter we used a different symbol. I used U, but you see, don't fall for this symbolism. Okay. Maxwell. By that time, this quantum physics was not known. By his time, everything was a wave. Light was a wave. EM wave was still a wave. And then de Broglie, and then Planck and Einstein. How the things converged. Things actually converged. Okay. This E over c. This is equal to E over c. So what is E? E. Now this E, in this expression, E is energy of photon, M is mass of photon. Mass of photon. Okay. And that's it. We have to stop here. We have to stop here. If I try to explain anything more, I am definitely going to be wrong. Absolutely wrong. Okay. You just note this down and do not try to find too many meanings from all this. You just note it down and remember it and memorize it. Okay. Do not try to find any other meaning from these statements. Okay. But remember, this mass of a photon is not the same mass that we actually think of, that we usually attach it with some object. It is not the same mass. This mass has quantum mechanical meaning. This mass can be understood only under the umbrella of quantum mechanics. Okay. Classical mechanics. If you try to relate this concept with the classical concept of mass, you are bound to go wrong. Okay. This is not the same mass that we usually think of in classical mechanics, classical physics. Okay. Get this point. Okay. So you just note it down and that's it. Stop here. Okay. Photon is in quantum mechanics like we have elementary particles. I have electron. Electron is an elementary particle. In the same way, photon is also an elementary particle in quantum mechanics. Okay, so note it down and that's it. Do not think too much about it, because if you think too much about it, you are definitely going to be wrong about it. Okay, because to really understand all these things, you have to study quantum mechanics. All of these things have quantum mechanical significance, no classical significance. Okay. Now let's see. Okay, let's do some problems. Then things will slowly start to settle down. Let's start with this first question. Calculate wavelength of first a particle of mass 1 gram moving with 1 meter per second. A very small, let's say a dust particle, a very small particle, 1 gram, moving slowly 1 meter per second. A particle is also a wave. Its wavelength will be given by de Broglie. Okay, he is going to give us the wavelength. Okay, we have to find it. Now, second, an electron moving with let's say 10.6 meter per second. We will do it. We will do these problems. Next, energy of photon. Energy of a photon is equal to kinetic energy of an electron. Okay, energy of a photon is equal to kinetic energy of an electron. Okay, what is relation between their wavelengths? Okay, let's do few problems. Okay, let's see. Okay, now here third one. Okay, YDSC is carried out with beam of electrons. Okay, so I have this YDSC setup. Okay, and it is carried out with beam of electrons. So I have this fast moving electrons incident on this setup here. Okay, this distance here, the usual symbols, the distance between the slits is small d and this is capital D, let's say. Okay, so they are going to interfere. Particles are going to interfere because it behaves like a wave also. Okay, so IDSC is carried out with beam of electrons. Okay, find wavelength. Find not wavelength but fringe width. Find fringe width. If first electrons are moving with speed v, okay, so I have this electron, mass of electron is m, some condition is given, so they are moving with speed v, so and they are incident on this YDSC setup, so they will produce fringe pattern. There will be certain fringe width. What will be fringe width? Okay, and second, so find fringe width if electrons are accelerated from rest through potential difference, potential difference of delta V. Okay, let's answer these, and then we will do more. We will do more problems. Okay, many more. Find out. It should be easy. First question here. Okay, I have this h over p. So it is equal to h over n v. Okay, now the first case, lambda is equal to h, 6.626 and 10 minus 34 over, mass is 1 gram, so 1 gram in kilogram will be 10 minus 3, this is mass, and the speed is 1, that's it. What it is? It is 6.626 and 10 minus 31 meter. A very small distance, very small distance. Something that cannot be measured. Cannot be measured, so small. The particle indeed behaves like a wave, but the wavelength is very small. This is something that we cannot measure at this stage. The stage in which our human civilization is. Right now we are not yet so advanced to measure this value. In future it could become possible. You will see. It will be found to be correct, absolutely. Okay. Every prediction made by the quantum mechanics, no matter how weird, how nonsensical and ridiculous it seems to be, but it's found to be correct. Okay? Now, second, this is the same thing here, 6 over, okay, we need the mass of electron, okay? You can take this value, 9 and 10 minus 31, okay, kilogram, this is kilogram here, okay? Use this value, and 10 minus 34 here, and here I have 9 and 10 minus 31, and 10, 6, okay, speed. So we have this approximate answer, it's like this. So 6.6 over 9 and 10 and 10, you see this becomes, it goes up here, becomes minus 3 combined with 6, minus 9, 10 minus 9, okay. This is approximately equal to, I can take this as 10, okay. So approximately 6 and 10 minus 10. This is 6 angstrom. Now this is something which is within our reach. This is within our reach. Okay, we can actually verify this. And of course it has been verified. Okay. So this is that's how it is. Wavelength of electron. Now second one. Try to do this. Let's see what answer you get. Energy of photon, okay, energy of photon is equal to hc over lambda. Hc over lambda. This is what is this? This is energy of photon, okay. Energy of electron, kinetic energy of electron, okay. Or let me write it like this. Energy of photon is equal to kinetic energy of electron. Let me write it like this. Okay. This is hc over lambda of photon is equal to half mv square. Half mv square. That's it. Now, I want to find wavelength. Wavelength is going to be equal to wavelength of electron or any particle, it is going to be equal to h over p. This I can write as under root of 2mk. K is kinetic energy. Can I do it this way? Okay. Of course we can do it. We can do it this way. Okay. So that's how it is. This is equal to, so kinetic energy. Okay. So lambda square is equal to h square over 2m and k. Okay, so k is equal to h square over 2m lambda square. So I can write it here. This is going to be equal to h square over 2m lambda electron square. That's it. We have this answer. Okay, this 1 power of h gets cancelled. I get this relation: lambda electron square over lambda of photon is equal to h over 2mc. That is one relation, okay? Relation between these. Wavelength of both, photon and electron. Now here, what is fringe width? Do you remember it? What is fringe width? Okay. What is fringe width? Let's first write this thing here. Okay. In question number 3. Find fringe width. If some things are given, okay, it's like this. So I have lambda is equal to h over p. is h over mv, okay, is equal to h over under root of 2mk is h over, okay. So I hope that you know how to attend this class. After every problem, the moment I write the problem, you have to pause the video. You don't have to watch it like a movie. This is not an entertainment, okay? I hope that, I'm sure you should have realized it. So, okay, after every problem I write, you have to pause the video. Forget about me, forget about the video, okay? Try to get some answer. Whatever comes to your mind, don't worry about it. Whatever comes to your mind, you apply that. You applied that, do not worry about it being right or wrong. That's not your job to worry about. Okay, whatever comes to your head, you just apply that. And then let's see if you are doing it right or not. Okay. Kinetic energy. A charged particle, an electron, accelerated through some potential difference. What it does, it gains kinetic energy. We have done all these concepts, okay. Now there is nothing new that we need to do. In electrostatics, in potential and all that, we have been doing so many things. Okay, so I just have to write, so when a charge is accelerated through a potential difference, it is going to gain kinetic energy. Equal to what? Okay, this gaining kinetic energy is equal to Q times delta V. Okay, so here it is accelerated from rest. So initially it did not have any energy. So its energy is going to be equal to 2m and E times delta V. Okay, now what is fringe width? Fringe width omega, okay, it is lambda capital D over small d. Okay, so that's it. These two are given, capital D, small d. These two are given. Okay, and lambda. I can write lambda. In terms of speed, I will write this expression. In terms of potential difference, I will write. That's it. That's my answer. Okay, that's how we do it. Okay, let's do few other problems. Okay, next problem. What is the energy and mass? What is the energy and mass of a photon of wavelength, let's say 500 nanometer. Okay, try to get this answer. You know all the required values. You know the value of H. I wrote it in the beginning. You should have noted it. Planck's constant. Generally, in your exams, all the standard universal constants, they are given. But if you remember it, then it's good. Okay, it's not a problem. Even if you don't remember, it's not a problem, because in exams generally they provide. If they ask this question, chances are they will give you. Okay, the value of H and all that. Okay. So what is energy and mass of a photon of wavelength is? Okay. What is energy? Energy is equal to h nu. Energy is h nu. Okay. This I can write as hc over lambda. Hc over lambda. Okay. So what it is going to be? Okay. What is energy? Okay. In electron volt. You know that electron volt is also a unit of energy. Okay, let me write it just in case you forgot it. 1 electron volt is equal to 1.6 and 10 minus 19 joule. Okay, this is the unit of energy that is used in atomic and nuclear physics, in modern physics. Okay, so most of the problems, not most of them, but almost all of the problems that we are now going to do In this chapter and in the remaining all the chapters of modern physics, we are going to use this thing, okay, the energy of unit electron volt. So this is something that you have to remember, 1 electron volt. Okay, and then we explained it also. What is 1 electron volt? When an electron is accelerated, okay, delta K is equal to Q delta V. Okay, this is E, and this becomes 1 volt. This becomes 1 electron volt. It's like this. If I accelerate one electron from rest, if I accelerate one electron from rest through a potential difference of 1 volt, then its kinetic energy will become 1 electron volt. And that is equal to this. Okay? Okay, understand this? All of these things we have discussed it already. That's why I am not really going to explain too much about it. Okay? We have done these things already in previous chapters. Okay? So I expect that you are still able to retain. Okay, we are towards the end of this course, but I expect that you have retained at least the crucial ones. Okay, so this is it. So this is equal to HC. So 6 and 6 to 6. Okay, 10 30, minus 34. And this is 3 and 10 8. 5 and 10 minus 7. What is this? This will be in Joule. Everything I am writing in SI. Answer also I am going to get in SI. This will be in Joule. This is energy of photon. Okay. Now, let's simplify this. So this becomes 0.6. Okay. So this is it's approximately like this. 3.97 and 48, all of that. And 10, you see this becomes 15. This becomes 15, 7 and 8, 15, and combined with this, it becomes minus 19 joule. This many joules, okay? And this will be equal to 3.97 something, 10 minus 19 over 1.6 and 10 minus 19 electron volt. Okay? Now this will be approximate answer, okay? Approximately it is going to be 2 electron volt, not 2. Let me take this as 4, okay? So 40 over 16, 4 and 10, approximately 2.5 electron volt. Okay, approximately 2.5 electron volt. Okay, let me keep this value here. Let me keep this. Energy is 2.5 electron volt. And remember, this is an approximate answer. What about mass? Okay, so I can write this E is equal to mc square. Okay, so m is under root of E over c square. Okay, I can also write it like this. Okay, this lambda is equal to h over p, or let me write it like this: p is h over lambda. Now this p is mc, is h over lambda. So this you see this mass is h over lambda times c. Okay, lambda times c. Okay, this I can write as hc over lambda c square. Okay, hc and lambda here. This is E. So E over c square. This is mass. Now why under root? No, there is no under root. E over c square. You just put these values and you get the answer. So what is the mass? Okay, let's have some idea. This mass is going to be equal to, this is the energy, 3.97 and all that, 10 minus 19 over c square, 9 and 10 power 16. Okay, this is approximately going to be 4 or 0.4. Okay, or 0.45, whatever you like. Okay, we are just approximating it. So and 10, this goes up, becomes minus 35 kilogram. Okay. Mass of electron is approximately, okay. So this is going to be, okay, so this is equal to 4.5 and 10 minus 36 kilogram. Okay. Mass of electron is approximately 9 and 10 power minus 31 kilogram. We just used this value in the first problem, if you remember. Okay. So this is how many times? 10,000. No, not 10,000. 100,000 times. 100,000 times lighter than mass of electron. But this comparison is actually absurd. Okay. I'm emphasizing this point again and again. Do not attach any meaning to this. We got some answer, then that's it. Forget about it. Question was asked, I know the formula, I got some answer, and that's it. I cannot actually compare this mass with this mass here, okay, because they have different meaning. This can be explained only by quantum mechanics, never by classical mechanics. Okay, so you have to keep this thing in mind. So never attach, never try to discover your own formulas. Never try to discover some new relations, okay, using this half-baked knowledge. Okay, keep that thing in mind. Whatever is written, 3-4 formulas, you just accept only those. That's it. Forget everything else. Do not discover your own. You are going to be wrong. Okay. Now, after this, a very important question. Very important question. Okay. It's like this. Okay. First, what is? I am keeping this problem. Okay. We are going to do something with it. What is, first of all, what is unit of HC? Simple problem. What is unit of HC? That's it. Okay. Now find its value. Find values of HC in terms of, in units of joule meter. Okay. In units of joule meter. Okay. Joule nanometer and joule electron volt nanometer. Do this problem. Try to get some approximate answer. Okay. You know how to do this. You have to stop the video, get some answer. Now we are going to discuss it. HC, energy, is equal to HC over lambda. Okay, so what is HC? It's E times lambda. This is joule. So SI unit will be joule and meter. HC. What is so special about it? Very special. Okay. Just treat it as a very special thing. HC. It is going to make our life easier. Very easier. Very easy. Okay. That's why it becomes important for me. Now, if this is joule meter, I can also write it in joule centimeter. The other units, this is SI. I can also write it as joule and nanometer. I can write it as electron volt meter. I can write it as electron volt angstrom. Anything, electron volt and nanometer. Okay. Now I have to find this value, the numerical value, in terms of this unit here, joule meter, then joule nanometer and electron volt nanometer. Okay, let's try to get some answer, some approximate, some estimate. Okay, it's like this. HC. Okay, let's start from here. So HC is 6 and 6 to 6 and 10, 34 and 3, 10, 8. Now this is going to be in SI. It is going to be in SI. So it's like 78 here. It's like this. 19.8 and 10, minus 26. Minus 26 joule and meter. Joule and meter. Makes sense. Pretty easy. Nothing much. Okay. Now, this I can write as 19.878. You see, all of these are approximate values because even the speed of light is not exactly that. Okay, somewhat lower, but not that. Okay, and 10 minus 26 and 10 9. Then this becomes joule and nanometer. Joule and nanometer. Okay, 1 meter is 10 9 nanometer. Okay, so I got it in this, I got it in this. Now what about electron volt? Okay, it will be 19878 and 10. Okay, this is how much? This will be minus 17 over 1.6 and 10 minus 19. This will be electron volt nanometer. Electron volt nanometer. This is HC. Okay. You do all of this calculation. Okay. You are going to get it approximately as 1238 electron volt nanometer. This is HC. Okay. We can take it as to simplify. Okay. This is just approximate value. Just approximate. Okay. If you use the proper correct values here, you are going to get somewhat different. Okay. But we are not bothered about that. We are not really bothered about that. Okay. To simplify calculations, okay, we generally take it as HC is equal to 1240 electron volt nanometer. Some people also take it as 1242. Okay. And now if it is approximate, whether I take it as 1240 or 1239 or 1242, it does not really make much difference. Okay. So according to the problem, if you think that taking this value, my problem calculation is going to be easy, you take this value. If you think that taking this value as 1242, my calculation is going to be easy, take that value. Okay, it's not a problem. Okay. But remember this. Remember this. If you remember this, you are never going to be more thankful for this value here. Okay. You are always going to be thankful, always, that you remember this thing. Drill it into your mind. Okay. What is the use of this? Let's see the use of this. Okay. What is energy here? In this problem, let's go back to the first problem here. This energy is equal to Hc over lambda. What is value of Hc? From here I will write 1240 electron volt nanometer divided by wavelength I will write in nanometer. This is 500 nanometer. What do I get? What do I get? I get 2.48 electron volt. Look at this and look at this. Same answer. Both are actually same because both are approximated. Okay. So both are same. Okay. You understand this? Okay, let's do one more problem. And then in the next class, we will start doing what? We will start the photoelectric effect next lecture. So let's complete this lecture. Let's complete this thing. From the next lecture, we will immediately start a photoelectric effect. Okay. Okay. Question is like this: a laser beam a laser beam of intensity, okay, let's say 5 watt per meter square. Okay, a laser beam of certain intensity, not only 5, okay, this 5 will be like small, 10 power 5 watt per meter square. Okay, I have this laser beam and wavelength 6200 angstrom. 6200 angstrom. Okay, falls normally on a surface of area 1 centimeter square. Okay, calculate first number of photons striking the surface per second, first of all, and second, force applied by beam on surface. Okay, can you find it? Can you find it? Intensity 10 power 5 watt per meter square. That is intensity. Wavelength is given. It falls normally. So I have this surface, 1 centimeter square surface. Light beam is hitting it normally. So photons are arriving at the surface every second. How many photons per second? We just have to estimate. Not calculate, but I think it will be more proper if I call it estimate. Find some estimate, some rough value. Okay. Okay, you know what to do. You have to pause the video, stop the video, forget about the video. Okay? Get some answer. Whatever comes to your mind, get it. Get the answer. And then we are going to solve it. After the lecture, you will open up the problem sheet, solve problems, every problem. Whichever problem you are facing difficulty, we are going to discuss it. Okay? During discussion, okay? You understand that this is a holistic course. Holistic, complete in every respect. Okay? But then it requires certain efforts from your side. Not only certain, but equal effort. Okay? Okay, let's try to understand this. Intensity. What is intensity? Intensity is energy per unit area per unit time. Okay? Energy per unit area per unit time. What is energy? Intensity times area times time. Okay. In 1 second. Okay. Energy arriving at surface. Okay. E is equal to I. What is I? I is 10 power 5. 10 power 5 times. What is area? 10 minus 4. 1 centimeter square into 1. This becomes 10 joule. In 1 second. In 1 second, 10 joules of energy is arriving at the surface. It is arriving in form of photons. How many photons? To find that, I need to look at the energy of one photon. Energy of one photon, okay? Energy of one photon. Energy of one photon, okay, is equal to hc over lambda. Now here I am going to find use of whatever we derived in the last problem. 1240 electron volt nanometer lambda. This is in angstrom. I can write it as 620 nanometer. Okay, is it not double of that? This is 2 electron volt. 2 electron volt. Okay, this will be 2 and 1.6 and 10 minus 19 joule. What is this? This is energy of one photon. One photon. This much energy arrives. Energy of one photon is this. Number of photons. Okay. Number of photons. N is equal to 10 over 2 and 1.6 and 10 minus 19. Okay. This is going to be equal to 5 over 1.6 and 10 19. Approximately it is going to be equal to 3 and 10 19 number. A huge number of photons. Okay, gigantic amount of photons arriving in 1 second. 1 second, and just in this small area, 1 centimeter square. This is 1 centimeter square. Okay, 1 centimeter square. That's it. In only this much area, these many photons are arriving in 1 second. Now, the second one, force. So, photons are arriving. Okay, let me see. I forgot to do that. I hope that it was focused well throughout this lecture. Sometimes this focus gets disturbed. I need to keep on checking it. Okay. Anyway, we have some time. Okay, time is up. Okay. Anyway, let's complete this. It's going to take a little bit more time. Force applied by beam on a surface. Why there will be a force? First of all, why there will be a force? Because photons are striking the surface. It's like hitting this surface with balls, with particles. Particles have momentum. Particles have momentum. Okay, particles have momentum. Okay, and then they hit the surface, momentum changes. Okay, so I have certain momentum here. Okay, this is my photon. Okay, it has certain momentum here, h over lambda, Okay, force applied by beam on a surface. Okay, assuming. Okay, I need to specify this. Assuming. Okay, assuming. Beam is reflected. Okay, let's say beam is reflected completely, 100% reflection. Beam is completely reflected, 100% reflection. Okay, so now it is bouncing back. It is bouncing back with same momentum h over lambda. What is delta p? What is delta p? It is equal to 2 times of h over lambda. Something that I don't need to explain. By now you must have been very comfortable with all these things. This is changing momentum, 2h over lambda. Okay, now what will be force? Force is dq over dt. This is just for one photon. This thing is just for one photon. Okay. I have these many photons striking per second. Okay, what if I have n number of photons? It's like d over dt. Okay, n times p. What is p? Changing momentum is a 2h over lambda here. This is changing momentum. Okay, for one particle. Okay, I can write it this way. Okay. And this with some arrangement, I can write it like this: 2h over lambda and dn over dt. dn over dt. Now, does that make sense? Does that make sense? Okay. Are you getting confused? Are you getting confused with this symbolism and all? Because this also is a change, and this also is a change. Okay, so I think I need to kind of use some other symbol. I am sure that you must be getting confused. Let me write like this. Then maybe it makes more sense. Okay, one photon. This is for one photon. For one photon. Okay. No, this is a general expression. This will be equal to 2h over lambda over delta t. Now this is for one photon. For one photon. Okay. Sometimes you see this way of writing becomes confusing. I think this is more proper way of doing it. Okay. Now this is n times 2h over lambda over delta t. This is for n photons. N photons. Okay. Now this I can write as 2h over lambda and n over delta t. Now this makes some sense. Rate of striking the photons. At what rate the photons are striking? Okay, this I know already. It is 3 and 10 power 19 per second. Per second. All of this calculation we did it for 1 second. So this final value is per second. These many photons per second is striking this surface. This is going to be force. Average force. Okay. Let's estimate it. Let's estimate this. Okay. Let's estimate this average force 2h over lambda. How can I make my life easy? 2hc over. I can make my life easy like this. Okay. And n over delta t. Let me keep it separately. Now this thing I know. hc over lambda. This thing I know. Okay. It is 2 electron volt. This I know. Okay. I will change this into SI. Okay. SI. So this is 2 times 2 electron volt. I will write 1.6 and 10 minus 19 joule divided by C 3 and 10 8, and then this value here. Okay, it is 3 and 10 19. Okay. This is going to be 6.4 and 10 minus 8 Newton. 6.4, 10 minus 8 Newton. Okay. All right. Got the same answer. Look at that. Look at this. Now you look at this. Momentum of EM wave. Something that we are driving this using the concept from this chapter. Now look at this. Momentum of EM wave. Okay. Maxwell, what did he say? Maxwell, what is momentum? It is equal to E over C. Maxwell said it. Okay. In the beginning also we derived it. We have written the same thing. But then that was from the quantum mechanics. This is from classical mechanics. Maxwell's theory is classical physics. Maxwell's theory of electromagnetism is part of classical physics. He calculated this thing based on his theoretical calculations, purely mathematical. Later on, quantum mechanics was also giving the same thing. So things converged. Okay. Now, in the same chapter, if you understand it, towards the end of this chapter, which chapter? EM waves. We were doing this problem. Okay, where electromagnetic wave is hitting a plate. Then what will be force and what will be pressure? Okay, the pressure. Okay, pressure P is equal to. Okay, if I have this wave, this is my wave. It is hitting this surface here. Okay, then we said that this force is equal to dP over dt. First of all, this becomes equal to 2 times of E over C and dt. Okay, and what is pressure? Pressure, capital P, small p here, capital P is equal to force over area. Okay, over area, and this is 2 times of E over C and A and dt. Now this thing here, energy per unit time per unit area, this becomes intensity. We write it as 2I over C. It is in this case where when it gets totally deflected. We derived this relation, we did this problem. When? In electromagnetic wave, towards the end, I think in the last lecture, we did it. Okay. Or we generally write it like this. dP, P is E, so we write it like this, dE. Okay, so that you are not confused. Okay. Here dP is equal to 2 times of dE over C. Okay, the momentum is P here, momentum is P here. This momentum is E over C. This momentum is also E over C. Okay, so change in momentum, delta P is 2 times of E over C. It's like this. Okay, do not worry about too much about the symbols, the meaning of. Okay, look at the concept, the theory. Do not worry about whether I should write delta or I should write D or delta. Do not be confused. That is not of much importance here. We have done all of these things properly in chapter on EM waves. Okay, I'm just trying to remind you. I'm trying to help you recall those things. So this is pressure. What is force? Force will be equal to pressure into area. This will be 2I over C times area. 2. Intensity 10 power 5 over 3 and 10 power 8 and 10 minus 4. This is 2 over 3, or let me write it as 20 over 3 and 10 power. Okay. So this becomes 20 here minus 8. Minus 8 Newton. What a coincidence. This is same. This is 6.67. 6.67 10 minus 8. This also is same. It appears different just because this contains too many approximations. Okay? Look at this. Try to make this connection. Connect the dots. When you are able to connect the dots, different dots together, that's the moment you start developing intuition. And that's the moment when you find yourself in sync with this course. Okay? Okay, so that's it. Let's conclude here. Next lecture we start photoelectric effect. Okay.